me, I have a little bit of a cold, but I hope my voice will last at least for the next 60 minutes. As I announced on Monday, I have 3 lectures, and they are on the theme of the ichthyosaur. So the ichthyosaur is this fish dinosaur that Schrödinger likened to the single quantum system, saying that we will never do experiments on a single quantum system, just as we will never raise the ichthyosaur in the zoo. But now we are actually doing experiments with the single quantum systems. And on Monday I described, I gave a few examples of how we treat the single quantum system under continuous observation by what we call quantum trajectories. Then my plan was to spend today discussing what we can teach our ichthyosaur. How can we use the measurement and actually discipline that teach tricks to the quantum systems. And then my plan for tomorrow would be to use the ichthyosaur as a tracking dog, that is as a sensing device. But given the very nice introductions we had yesterday from Christian and also from Maury, I figured that maybe it would actually be a good idea to switch these 2 topics. So in fact, what I will do is that I'll give my Thursday lecture now. So I'll talk about sensing, following up on the very good introduction we had to this topic yesterday. And then tomorrow I will go and talk about the training of the ichthyosaur and studying the quantum dynamics that we can engineer and monitor of quantum systems. So we will now go to the sensing or measurement, which is also in the title both of my general theme here, but also this whole winter school course. So this is maybe very fitting to the outside view. This is the good, the bad, and the ugly, the clean, easy. I'm going to talk about the good, the better, and the best, at least theoretically best, precision measurements that we can do with quantum systems. So there are good ways, and there are even better ways, and there are the optimal way where you can extract the most possible information about Hamiltonian parameters or environmental degrees of freedom that interact with your quantum system. So this is really the theme of this presentation. So here is just a small distinction. It's not very important, but I will sort of sometimes talk about one, sometimes the other one. There's something that's called parameter estimation, and there's something that we call hypothesis testing. Parameter estimation is when you have a Hamiltonian in which there's a single parameter you want to estimate. That could be a detuning of frequency or a coupling strength. And by doing your measurement on a quantum system, you may find out what is that parameter. The hypothesis testing is where you actually know discrete candidate values, but you want to know which one applies. Okay? So that's 2 hypotheses, and we want to distinguish between the 2. And of course the 2 are related, because you do measurements on a quantum system, and you want to infer which one is the right one. And you might even say that parameter estimation is hypothesis testing if you lay out a fine grid of candidate values for your parameter, and you treat them as separate hypotheses. So instead of having 2, you could have maybe 100 candidate values of theta spanning a whole interval, and then you will actually check which of these 100 hypotheses is the right one. So they are intimately related, but the way we discuss what we're trying to do is somewhat different. So here's a quantum state. It's actually many spins forming a large collective spin whose wave function could look like that in a kind of collective spin representation. And this is the initial state, and you may drive it into a final state by your Hamiltonian. So the final quantum state looks like this. If you are subject to a particular Hamiltonian, of course, it doesn't help us much that there's a quantum state who looks like something. I have to do a measurement on the system. So if I measure, for example, this vertical spin component, then this particular state will give rise to some kind of histogram of events if I do many measurements. Yesterday, both Christian and Maury talked about experiments where you have 2 outcomes. And then you could do the measurement many times, and then you could ask how many times do I get spin up, how many times do I get spin down. But if you have a large spin, you can have 100 different eigenvalues. And you have to ask yourself, how many times do I get any of these 100 eigenvalues? And in a real experiment, you are then going to get this histogram. And based on matching that histogram to what you actually expect from different states, you can estimate the Hamiltonian parameter. And I'm going to tell you a little bit more about how we do that. And the parameter theta you estimate will of course not be precisely estimated if you only have a finite number of detections. There's going to be an error bar, and that error bar will go as 1 over the square root of the number of experiments you do. That's what we learned in lab course too. And what interests me is really this prefect. I mean, how does it scale with 1 over the square root of the number of experiments? What is it that governs, what is that value of that prefect? So this is the parameter estimation. We try to make it as good an estimate as possible, and And we saw examples yesterday when we Moelmer wanted to estimate the rotation angle of a spin, and you could estimate that very precisely, in particular if your spin went up into more like 50-50 superposition of the ground and excited state, because then you would be very sensitive to further rotation of the spin in terms of the populations of the spins. This is for the parameter estimation. You can also say if there are two hypotheses, then you want to minimize the probability of making a wrong guess. So somebody actually turned on a 0, and after the measurement, I'm going to guess which one was the right one, and I want to guess correctly as many times as possible. So how can I do that? And that's the number I want to minimize if I want to do the better or best hypothesis testing. Now, the information we get is really from this data. So this is the data record. So I want to minimize this error probability, or this A factor here. And it's really based on what is the distance between my expected outcome of measurement between different candidate values of my Hamiltonian, for example. So of course it doesn't work at all if two different Hamiltonians give rise to exactly the same distribution, then my measurements cannot distinguish them at all. But if they give rise to two very different distributions, then I should have a good chance of seeing what of the two is the right one. So yesterday, Christian showed this. I'm just copying the essential argument. If you have only two outcomes, you can count how often do you get one in 0, and how often do you get the other one in 1. And maybe you have a theory who says that the ratio of N1 to the total should be some probability, which should be a function of the parameter you want to estimate. Yesterday, this probability was cosine squared theta, because it was the excited state population of a system who's doing Rabi oscillations with the angle theta. So therefore, you have a connection here between, for example, Rabi frequency and this counting. But what we also learned yesterday was that these numbers are the ones you get in the experiment, but you could have gotten a little bit more or less because there are natural fluctuations in these numbers. There could be a binomial distribution. There would be a typical error bar, and a typical error bar in that number too. That of course means that you're not really measuring precisely that value. You're measuring that value plus minus whatever is hiding under these error bars. And that means that there's going to be an error on this measurement. And that error goes as 1 over the square root of the total number of measurements, as we saw actually twice yesterday. So this is really the same thing that I will now move to the more complicated case where there are more outcomes of the measurement. So instead of having 2 columns, I have 100 columns. And I have a count in each of these 100 columns corresponding to the different eigenvalues of the JZ spin component if this is a big spin. But it could really be anything you measure, and later on you will see that I'm going to put completely different things on this axis in connection with my trajectory pictures. But it's the same story, that there is, for one value of this Hamiltonian, there's maybe a predicted distribution who looks like this. Okay, this was made by hand this morning in my room, and maybe for another value it should look like that. And now I ask you, based on the blue data, which is the most likely of those 2 hypotheses? That's what we really want to do, if it's hypothesis testing. And if it's parameter estimation, I would like to redraw the red curve with a slightly modified value of the parameter, and just see if I can really distinguish 2 nearby distributions, because they only change infinitesimally if I only change my theta infinitesimally. But there will be a relationship between the outcome and it. So this is of course a difficult problem, but the answer is that the error that you get on here really goes as 1 over the square root of the number of experiments you do, and the factor is itself 1 over the square root of something called the Fisher information. So the Fisher information is the statistical measure for how these curves depend on the parameter you're looking at. Okay? And that relation that you get, this 1 over square root of f, is called a Kramer-Mau bound, and that's a statistical thing. It has nothing to do with quantum mechanics. It's a general thing about how you can estimate something which comes out with noisy data. I'll show you the formula for the Fisher information, but you really don't have to care what it looks like, because we're not going to do any calculations of the Fisher information. I just want to tell you that it exists. So here it is. It says that if you know the likelihood, which is the same as the probability, for getting a certain data value, for example, this sequence of this histogram, if you know how that likelihood depends on the parameter, then taking the derivative with respect to that parameter shows you that there's a dependence on that parameter. Of course, we need this thing to depend on that parameter, otherwise we cannot sense anything. So this relation actually taking the derivative with respect to the parameter of the second derivative and weighting with the probability itself for how often you actually get that outcome. That will give you this Fisher information. Okay. And of course you can say, why is it the log and why is it like that? And there are different reasons that it has exactly this form. Part of why it's the log is that if you take the derivative of the log, you know you actually get the same as the derivative of this thing divided by the inside argument coming out here square. And that factor coming out is actually playing the role of weighting the statistics correct. If you have large count numbers, you also have relatively smaller errors. And that's exactly perhaps by this logarithm form. But it's really not important. I just want to tell you that if you have data who have a probability distribution, then just know that probability distribution is enough to tell you what is the error bar. And I can apply this one to the case with the two outcomes, 0 and 1, that we saw yesterday in the two talks. And then I get exactly what we learned yesterday as the error estimate of this thing. Of course, you heard a much more intuitive and much clearer explanation of how the number of fluctuations being binomial, how the slope of this curve translates into the error bar down here. But that gives exactly the same as if you do this calculation. But this one is ready for bigger challenges, right? Where it's really difficult to reason by hand. So it exists, this Fisher information. That is, you know, everything I do here is analyzing the outcome of a real experiment. I have to decide which observable I'm measuring, and then I'm relating to the probability distribution and the histogram of events to estimate my parameter. Now I want to mention to you the best hypothesis testing, or the best parameter estimation. That's one in which the Hamiltonian affects the state of the system. And I'm only asking, how can I actually distinguish that state from other states? I'm not talking about any particular measurement, because there might be one measurement who is smarter than another measurement. Maybe it's a really stupid idea to measure the JZ. Maybe I should measure the JZ projection along some other angle, or J projection along some other angle. Maybe I should not even measure that, but a completely different observer. Right? So if I want to ask that kind of question, it's more a question about how different are the quantum states. And then after that, of course, there's a challenge to find the measurement, the actual measurement you should do, who can exhaust that information. There are experiments where the certain observer doesn't tell you anything about the outcome. If Murray had taken his interferometer yesterday and measured the phase of the outgoing field, he wouldn't have learned anything, because the number count difference between the two output ports that carries the information he needed. So you can do really stupid measurements that teach you nothing, and you can maybe also find the optimal measurement. So that optimal measurement is a question about how close the states are. We still expect the error bar to go like this, but we can expect maybe this A to be smaller, because we now optimize overall measurement. And I'm not going to optimize in practice all measurements. That's an interesting exercise in itself. I'm going to just talk about distinguishability of quantum states. So the quantum Fisher information is really the one who asks, how does the wave function or the density matrix depend on the state? Or sorry, this argument theta that we're interested in. That's a very good question also to ask. And then you have to have a kind of theory who says, how well can you distinguish two different quantum states? What is the best measurement to do there? So the error, if it's the wrong assignment problem that interests you, then the error depends only on the overlap between those two states. Because if you have two quantum states and they are orthogonal, then this one is 0. And if they are orthogonal, they can be perfectly distinguished in a single experiment. You just have to measure, am I in one state or the other? And then you get yes or the other one, and that's it. That works. But it only works if they are orthogonal. If two states are not orthogonal, you cannot by a single measurement tell which one you actually occupy. So hypothesis testing actually just depends. There's only one number that can influence it, and that's the overlap between those two states. If you want to know your parameter theta, so I'm just looking for a small change in theta, then what is really relevant is to know what is the overlap between one state and the state where I have changed theta just a little bit. That state will have a modification which is exactly governed by the derivative of the state with respect to theta. So this overlap will tell you the sensitivity in parameter estimation. And if the function, for example, does not depend on theta at all, then you're not going to get anything, that's clear. And if the change of psi due to a change in theta is actually going to be not modifying the scalar problem, it's also not going to change the distinguishability between the two states. So that's the quantity we need to calculate. So here are two states, and I'm just drawing the pictorially as two vectors, and the angle between them is governed by the overlap between the two states. So if these two states are orthogonal, then I can just do a projective measurement in this basis, and then I know whether I have the blue or the red state. But if the states are non-orthogonal, I cannot distinguish with perfection if I'm in one or the other state. Just imagine that I ask, am I in the blue state? Of course, the blue state will say, yes, I'm in the blue state. But the red state will also say yes, with a probability, which is just a projection down in that state. So getting a yes outcome of that measurement doesn't really tell you that you are in the blue state. It tells you that perhaps you are in the blue state. If they are orthogonal changes, right, then it's impossible for the red one to say yes to that question, and then we are fine. You can play around what is the best measurement. And this is a super interesting question, because it has been interesting independent of the sensing and hypothesis testing. So back in the 70s, Hellstrom wrote a fantastic book about measurements in quantum physics. He was a somewhat isolated soul being captivated by that problem. And he wrote beautiful papers in this fantastic book. I mentioned one day a Russian scientist, Bilavkin, who was a similarly isolated Russian interested in condition dynamics. And in fact, those two became very good friends. And Slava told me that he learned to read English just to read actually Hellstrom's book. So anyway, Hellstrom showed that the best way to distinguish those two states is to find two other states who are orthogonal. One being as close as possible to the blue one, one being as close as possible to the red one. So you're just dividing the angle between the two, and then you go 45 degrees in both directions. And if you measure that state and assign that to the red outcome, and that one to the blue outcome, then you minimize this error probability. Then you will be right in the highest number of cases. So this is the best hypothesis testing you can ever do if you have to tell what state do you have. So it was very much about states now, but I just remind you, going back again, that those two states are the outcomes of time evolution with two different Hamiltonians. So when I have answered this question, I have also answered which was the two Hamiltonians, which one of the two was actually governed with dynamics. So this is an interesting thing, and the reason that people are getting really good at this now is that this is actually the same challenge as you face in quantum cryptography. If you want to steal a message being sent from Alice to Bob in quantum cryptography, you want to distinguish what is the state Bob sends. And he might exactly use bases who are not orthogonal to each other, sending photons who carry quantum information. And the eavesdropper's best attempt to actually guess what is being said is also this one. So there's a connection and an increased interest in this hypothesis testing coming from quantum information science, which is also very interesting. So this is the picture. Then of course in real life it might actually be quite difficult to realize not only what are these states, but what is the observer we have to measure to actually distinguish those two states. Yes?
So in this case, when you have two basis states, the red and blue, that aren't orthogonal,
yeah.
Is there any way that I can think of an NV system where the fluorescence is just either like 100% or 60%?
Yes.
Like that, in this
that could be exactly like that. Yes. So you could imagine, for example, an atom who has no transition to an excited state, and this one has a transition to the excited state. And then, of course, seeing fluorescence photons would say it could never be that one. But again, if these states were not orthogonal, so this would be a superposition of two such states, and this one would be the clean one, then you could actually get a click from any of them, and then you would not really know what happened. And then there's actually something crazy, and that's what I'm going to talk about. The rest of this talk is that kind of fluorescence measurement is not a single measurement. It's actually a continuous measurement because you keep illuminating the system. So therefore you are accumulating statistics, but with a caveat that of course you're also causing backaction in the system. So if I do the first click, I may actually project the red one into the blue one. So the next measurement is not on the original state, I may have already messed up with the system.
So would this suggest that for an NV system, instead of looking for dips in fluorescence, you should be distinguishing between full fluorescence and no fluorescence?
Yes, but again, you know, the little danger that already the first click has a back action, so that maybe the next clicks you get are actually just repeating the first thing you already got right. So we have to be very careful when we do this continuous thing. I think I can illustrate that also with the rest of the talk, but the fundamental issue in your question is of course exactly the right one. What should you really do? should you do a measurement on the system, if that's not the channel of interacting with the system, but the channel is that you have to hit it with a hammer, like we heard yesterday also in Christian's story, you have to see the light coming out, then that poses some restrictions. And can you make them match this crazy choice? And that's really a very good question. Yes?
So this is not a single measurement either, right? When you have two orthogonal bases, you still need to acquire statistics to distinguish between red and blue.
At least to meet to talk about these quantities up here. So of course, if you only get one example, so you get only one shot, then you might say, okay, like Clint Eastwood, do you feel lucky, Bob? So therefore, I can actually be lucky and make the right guess in one measurement. And if I put my challenge to be, give me one of the two states, give me one shot, and let me make a guess, and then if I'm right, you give me $1 million. Okay, then we can talk about it as a probability for actually getting that $1 million. But you're of course also right that that probability translates into the fraction of times I will be lucky if I do 1,000 measurements. And this group then is really the statistical statement saying that if you do this measurement many times, then you will be so precise, or you will be wrong so and so many times. So this is absolutely right. So now I've been talking a little bit about quantum systems, but I prepare an initial state, I evolve it, and then I do a measurement. And actually, as Maury discussed last night, already the preparation of the initial state is an interesting thing. So he could feed particular dual Fox state into his spectrometer, which would also give a higher sensitivity over here. So in this prepare, evolve, measure strategy, you should both optimize the initial state and the measurement you actually perform in the end. But now I want to switch to the trajectory, because it's actually very common in quantum physics, also as you are indicating, that we are not doing exactly that. Many experiments in spectroscopy, you are looking all the time. So that's a different story. That's a story where you are probing, for example, with a light field, a medium, and then you have a detector who's recording a time-dependent signal. And from that time-dependent signal, you want to infer what is that Hamiltonian parameter. So my time-dependent signal is going to be noisy, and based on that noisy signal, I'm going to infer the Hamiltonian parameter. It could be, I have an atomic gas, I measure the amount of absorption. The amount of absorption has something to do with whether I'm on resonance or not. Right? So I'm estimating the detuning parameter by checking how much is being absorbed in the gas. And if you measure, now what do you expect in terms of error bars? You do expect that the longer you measure, the more precise is your measurement. If this is a system who is has a steady state regime, then integrating for longer and longer and longer just keeps you informing more and more of the proper value of this particular quantity. So this is the expected outcome of such a measurement. The correct value, plus minus something that scales with time. The resource is time, the resource is not more systems. Yeah. And this could be the single NV center that you also refer to. So this has interested quite a number of people, including myself, for the past 15, 20 years, because we realized, of course, that the analysis of such a record is actually intimately connected to the analysis of these quantum trajectories. Because I'm doing the measurement continuously in time, I get random fluctuations, but the state also changes every time I get my random fluctuations. So there are correlations in this. So the typical lab course will tell you, please measure the mean value. And then from that mean value, you can infer what is the parameter. For example, the mean fluorescence from an atom is telling you whether you're on resonance or not. Okay. But there's more to it, because there are fluctuations. Associated with the fluctuations, there's back action on the system. The back action in the system imposes the presence of correlations in the signal. And those correlations play an important role in understanding what is that prefactor. Maybe all theories will tell me what is the theta estimating value, but the error bar really has much to do with the statistical fluctuations. And one thing in particular, you can say, well, if the system is roughly independent here, here, and here, then of course you can see the longer the time, the more of these independent measurements happen. So that immediately tells how big is this, or tells me that there's this routine dependence. But it doesn't tell me the prefactor, because it doesn't tell me how long I have to wait before I'm again independent from my previous measurements. So for this, we just have to make a theory. We have to make a Fisher information for this kind of sensing. And I'd like to show you how it is being done, again without being too formally technical, but just to give you a feeling for what is happening. So I showed you this picture before, but now I've added a new element. So we have a quantum system who is described by a wave function or density matrix, and I have measurements that I do on this quantum system. But now this system may be subject to different Hamiltonians, where there's some parameter, maybe one or more, who can take different values. It actually means that I don't have one wave function or one density matrix, because for each candidate value theta, there's a different evolution. So I should actually put a little theta here or here to indicate that for any choice of the Rabi frequency, there's of course a separate solution to the Schrödinger equation. And the measurements who come out, well, depending on the theta, I have a state who depends on the theta. Depending on the state, I have a probability to get my measurement result, because that's one rule. If you know the state, you also know the probability to get an outcome in the measurement. So there's a connection between the probability for the data I read and the parameter in the physical system. Of course there is, that's what it's all about. The fluorescent signal has an intensity who depends on the Hamiltonian, and of course that's what I'm going to see. But I'm going to completely exhaust from my data record how well as possible what is that theta value. So therefore I'm really going to use this trajectory approach that at every moment in time I get a new data value. That new data value will have some probability for occurring, and when I get it, there will be a certain back action on that state. It will have this trajectory dynamics, and therefore the next data value will have a correlation with the previous ones. And that's what we want to understand. As Morris told us last night, if you know the probability to get data conditioned on the parameter you want to measure, you can also go the other way. So there's a general reduction of the probability saying that if I know P of D given theta, I also, for a given measurement data, I get an updated value, what's the probability for that particular theta. So what Morris did yesterday was that he assumed maybe a uniform distribution for this theta, so you really don't know what it is. But then as you do your measurements, you gradually modify that distribution condition on what you measure. And I'll show you exactly how it works on the next slide. So this is Bayes. He was a priest in England in the 18th century. And the rule that Morris showed us also yesterday says that if you have two events, A and B, the probability for both of them being true can be either composed as a probability for one being true and the other one being true conditional on that one being true. And you can only have both right if one is right and the other one is right, and that will be right with a probability that is conditional on the first one. And the same you can also write it as B being right, and then A has to be right, and that's true with the probability, which is P of A conditional on B. So the Bayes rule will be applied by us here, where B is the unknown parameter and A is the data we observe. So there's a probability for getting the data given theta, and I want to translate that back to my probability of theta given the data, because that's how I'm shrinking this probability distribution until I know what it is. Or I find the most likely value, maybe the one that has the highest probability. Okay, so Bayes' rule is not here. Bayes' rule is what happens if I remove the middle term, because this immediately makes a mathematical equation, because the probability for theta given data and probability of data given theta. And this is exactly what we want. This is the uniform, or at least the prior distribution for the theta. Morris assumed it to be uniform, but of course there could be some reason to think that some values are more likely than others. This is Born's rule. This is the probability to get a certain outcome conditioned on the state that you have. This is the probability to actually get the outcome, but it doesn't matter because when you analyze the experiment, you know you have the outcome. So for us, it's actually just a normalization constant. But this guy is a really important thing. That's the probability of the theta given the data. So that's actually the new assigned probability to the different candidate values, conditioned on what you just learned. Okay. So the rule here says, take the prior one, assume, or not assume, but get from the experiment an actual data outcome, A, and then you just know this probability for Born's rule, you multiply that factor of the prior probability, and renormalize, and then you get the new P of B. Very nice. And that new P of B you set back over here, and then you make your next measurement, and your next measurement, and your next measurement. Because this is the prior probability before the next measurement. So you just keep updating. It's also called filtering, because you can assign a number of candidate values to theta, and then you're gradually modifying their relative probabilities as you do. Okay. So I'll show you here a simple example, which is related to the examples we saw yesterday, assume I have a spin here, and the spin can rotate at a certain angle, and then after the fixed time tau, I measure, are you still in the spin-up state? So the position of the spin-up and spin-down state with a cosine omega t factor and a sine omega t factor. I measure the spin along the z-axis at times integer times tau. So the probability that I get the same value as the previous time is going to be cosine squared omega t. So if I spin up, then after time tau, I will have an amplitude cosine omega tau here, so the probability is going to be exactly that value. If I should start in the spin down state, these two factors just change places. So it's always going to be this factor for keeping the state equal. So here's a simulated experiment. I start out in the spin up state, and the probability drops like the cosine square. Then I do the measurement, and the measurement was up, so therefore I return back to being up with certainty. And this is going on again and again. The first 5 detection events tell me that I'm in the up state. Then there's actually a measurement that puts me to the other state. Then I stay there for a few measurements. So you can see this is the sequence of, you can call it 1111000, or you can label it whatever way you like, but the change of states are the ones who are marked when you make these big transitions in the data set. Now, can I use this data set to estimate the value of omega? That's really what I want to do. So let me just try 3 hypotheses. Let me try a hypothesis which is the right one. So I hope I turn out to be right in the end. Half of that value and 3 half of that value. Okay? So these 3 candidate values, I give a prior equal probability of 1/3 all 3 of them. And then I'm asking myself, as these measurement data come in, what is happening to the 3 probabilities for these 3 values? So it looks like this. So the orange one is the low Rabi frequency, this blue dotted one is the higher one, and the black dashed one is actually the true one. So you see in the end, we are actually approaching almost certainty about the true value. But in the beginning, this is not so clear. But let me tell you what you see in the beginning, because that's actually pretty fun. You see, it didn't change state, it didn't change state, it didn't change state, it didn't change state. That's perfectly compatible with a vanishing Rabi frequency. It's actually more compatible with a low one than with a high one, because the lower the Rabi frequency, the more likely you are to stay. And experimentally, you actually stay. Right? So this is why this orange curve is climbing. Every time you don't change state, the orange one is going to get a little bit more likely. Right? And the blue one is getting less and less likely, because with such a high Rabi frequency, you should have changed the state by now. And it hasn't changed the state. And this dash one in the middle stays almost constant. Then, of course, it changes here, because now you have a click. And that click is not very likely with a low Rabi frequency. So therefore, the probability now drops dramatically for the orange one, because, oh gosh, it can actually switch the state. So this low value is not so likely anymore. The blue one increases, because suddenly, okay, now that's actually more likely with a high Rabi frequency. Of course, you should click now. And that is exactly what you see in periods with no click. The orange one climbs, the blue one descends, and then the clicks sort of recalibrate. And in the end, I can actually see the difference between those 3 values. So this is how this Bayes rule is applied here. And this is really exhausting the information in this data record. This is an easy example. Here's a little bit more complicated, but maybe more realistic example, namely the Rabi oscillations with emission of light. So now you're not measuring the atomic system, you're waiting for the photons to come out. And we saw yesterday that, of course, there's a mass, Monday, that there's a master equation, there's going to be dead Rabi oscillations if you don't look. But if you actually look for the detection, the atom is going to jump into the ground state and restart its Rabi oscillations over and over again. So I showed you this picture in my Monday lecture, where starting with the ground state, you do Rabi oscillation, click, go to the ground state, new Rabi oscillation, click, and go to the ground state. So there's a certain probability for living with no click for an amount of time. That probability, of course, depends on how strongly you drive the system. Because if you drive it very weakly, it's very likely you will see no click from the atom. If you drive it very strongly, there's a higher probability to get a click in the atom. So the no click is a little bit like the no state change story that I told you before. And then the click happens, and that teaches us something. Yes?
In the previous example,
yeah,
you have some period between the measurements and time. If the Rabi period is faster than n tau, and you're aliasing the measurement,
yes.
Can this stuff get at the higher frequency?
Yes. So and that's in fact, we have a small paper with this thing, and the paper is not really about this sensing issue. There are 2 receipts that are interesting. if you make tau very short, there's something called the Zener effect. This term actually goes to 1 very rapidly. And that means that for very frequent probing, you cannot distinguish the omegas because you suppress all the terms. So that's one regime, and we have exactly, as you say, the opposite regime, where if you make it too large, then you have an aliasing problem of the omega. And in fact, in that data, we sort of identify that it's a good idea to vary tau. So you can start with one size and then make it different, or randomly switch between two different sizes to kill both problems. So that's a brilliant question. Here, in this other case, nature is taking care of randomizing the times, because it's not us who make the measurement, it's the click events who come at random into our detector. Sometimes we wait long, sometimes we wait short for these click events. And this is a code that I have on the drive, so you can actually all play with that. And I encourage you to go and play with it because it's fun. So here is base counting, which is a MATLAB file, so if you run Octave, which is free, or you run MATLAB if you have it installed already. Then in this code, which is just, why is it always like that? I mean, it's on my screen. Is there any way to make this work actually? I mean, we have the same, let me just try and run it, but I'm a little bit, maybe the graph is going to display.
But the copy of screen.
What does that? Oh.
Fit win plus P.
Sorry?
Fit win plus P to copy the screen onto the project.
So it's control, P.
Windows.
Windows P. Yeah, and then what do I do? Duplicate? No. Extend? No.
Copy.
There's no word for this. Oh yeah, duplicate. Thank you very much. I hope you can help me back again afterwards. So the code. So now I can quickly show you. Maybe I should just run it again. No, I don't have to run it again. But what you see here. Okay, now I cannot move anything. Okay, good. So what the program is doing is that it assumes true values for the Rabi frequency 3 and 0, and then it runs the calculation. Actually, the 3 is the true value. So the click events you see are simulated with the true value, but this is a person who doesn't know which one is true. So he or she is actually propagating two states. One with the Rabi frequency of 3, one with the Rabi frequency of 0. And then when you move along, you can see that the probability, this is the probability for the two hypotheses, is growing. And that's the P1, that's the probability of having no Rabi frequency. And that one grows when there's no clicks. Because when you get no fluorescence, that's very compatible with the fact that you don't even excite the atom. So the longer the interval with no clicks is going to be, the more this one is growing, the more this one is going to descend. But then you get the click, and then of course, boom, you know the Rabi frequency cannot be 0. Bang, so therefore this one is now 0, this one is 1 forever after. So this is the very simple case because it's very easy to distinguish 0 and 3 Rabi frequencies. So let's make it a little bit harder. That's of course why we wrote the code like this. So now let's try to see if we can distinguish 2 and 3. So you see, now there's going to be clicks, but the clicks are not definitely killing one of the two probabilities. It's going to modify the weights between them, but after actually just 2 clicks, you actually accidentally are already in the case with a very high probability for the right outcome. And this third one really nails it down, and you definitely know you're now in the right state. So this is really, of course, accidental. You will also sometimes get click events that don't teach you very much. Let's just be a little more greedy here, and they go to 2.8 and 3. They're almost indistinguishable values. And you can also see that it's growing very slowly. But again, I can be fortunate and have this lucky event that is really ruling out one value in contrast to the other one. And sometimes you have to measure for longer, obviously in this case, than other times. And that's clear because if you want to discern two nearby values, you have to measure very long to see the difference. Yes?
So is this basically just a Photon process, or
yes.
Are you taking into consideration the fact that if you allow it to evolve for pi, and then you see a click?
That is exactly part of the story too.
Yeah.
So in fact, the little wiggles you see here, they are reflecting the underlying Rabi oscillations taking place. So that the simulations we do is really the full trajectory simulation where the click rate is proportional to the excited state probability, and the excited state probability is oscillating up and down due to the Rabi diet.
So it seems like you could just get lucky, and your first click could completely.
Precisely, because what you're suggesting is that if you have a Rabi oscillation that takes you perfectly back to the ground state with one Rabi frequency, but leaves some excitation with the other one, and you get a click exactly there, it has to be the one who left you excited at that point. The other one simply couldn't do it. And that's probably what is happening right there.
Yeah.
So this is what we see, and it's quite impressive and quite funny. Now let's see. Now it's getting exciting. Windows P, and then I just want to go back to, was it this one? Ooh, it's very exciting. So I should find my presentation. Okay, that was the wrong one. Windows P, PC, not duplicate, PC screen only. No. Extend. This should be right. Anything I can do here?
So you can click on your slides and just drag it over to the other screen.
But I don't see too. Yeah, okay, let's see what happened now. Okay. I don't dare go back to the MATLAB code unless I want to show you something more. But anyway, so this analysis, that's what we saw here also, just as you said. And of course, you can go all the way down here. At this point, you would never get a click to that Rabi frequency, but with another one, you could. So here is a sequence of clicks, and here's my two-level system again. If I have one Rabi frequency, the oscillations look like this. Here was one of the clicks, and there are some other clicks. If the Rabi frequency was lower, it doesn't change when the clicks occur, because they occur in the lab, so they're experimental data. But of course, as a theorist, if the Rabi frequency is lower, I know that the evolution should look like this. If the Rabi frequency is higher, the evolution should look like this. And if I arrange them underneath each other, then the clicks happen in all the same places in all these trajectories. And I don't know which one is the right picture, because I don't know which is the right Rabi frequency. But if I have these three candidate values, then I know that one of them is the right one. Which one is the most likely one? And you already gave away the answer. That's the one who is the most likely to give these clicks. So look here, this one is more excited at this moment than the other two, or at least at this one. So already at this click, this guy's going to pick up probability, and this guy's going to pick up probability, and this one's going to be suppressed. And then comes the next one, and the next one, and the next one. And in the end, this is going to be the most likely one after just few detection events, because any low value in any of these data down here suppress these guys heavily. So it doesn't take very many detector clicks to actually resolve the Rabi frequency in such an experiment. It takes a surprisingly low number of detector clicks. So this was my MATLAB code that we just run. And here's a quantitative statement about the waiting time distribution between clicks. This is accidentally the curve that Murray also calculated from this non-normalized wave function that he was treating. So if you have a certain Rabi frequency, that waiting time distribution should look like the red curve. And if you do really, really many experiments, you find this histogram that matches perfectly. If I wanted to check if I could have any other Rabi frequency compatible with the blue data, then these would have their periodicity here modified, so therefore they would be less good agreement. In fact, I can even calculate the Fisher information because my data has now been reduced to this histogram. And I can take the red curve here, and then I can calculate a similar curve for other Rabi frequencies, and I can use my Fisher information formula to tell how good is this actually at estimating the Rabi frequency, for example. So this formula I showed you before actually also applies to this histogram, and we can analytically, in these papers, calculate how good is counting to distinguish Rabi frequencies. Okay, this is very formal. In practice, we just do it. And here is a run where I have, let's say, a few dozen clicks, and I want to estimate what is the Rabi frequency right in there, two-level atom. The system has a steady state. So normally, in spectroscopy, you ask yourself, what is the excitation as function of Rabi frequency? And that's going to be a formula to tell you what it is. And that saturates very fast. So if your Rabi frequency is just a few times the line width of the transition, you will have 50% excitation in steady state. And it's very difficult to see the difference between a Rabi frequency of 2 and 5 and 11 and 500 in the total fluorescence signal, because it's going to be the same. And there's going to be an error bar, so if you only count 40 photons, you're going to be plus minus square root of 40, so that's like a 20% error. So this error bar tells you that you cannot see the difference between a Rabi frequency of 1 and infinity. just from the total count. But I'm now not using the total count. I'm using the actual click event, and I'm using my Bayes rule. And here you see, now you see, a fine grid of candidate values between 1 and 7. And after already 6, 7 clicks, I have ruled out lots of values, and I start converting to this being the most likely one, which is actually the right one. There's still some aliasing. So the click intervals here were also almost compatible with some higher value. And then this very long interval essentially kills these high frequency components. And then when time progresses, it gets better and better. But you know, this is astounding that you actually have, say, better than 10% estimate of the Rabi frequency after 10 clicks in your detector. And that's because we don't actually quantify the number of clicks, we quantify the intervals between the clicks. It's also crucial to understand that every click is having a back action in the system. It's due to that back action that we see this phenomenon. It's because every time you get a click, you start a new transient evolution of the atom. If you were always in steady state, there would not be this dynamics. These dynamical features is due to the fact that every click resets your system back in the ground state, and you start a new oscillation. It will be damped in the long time limit, but the next click will be before that long time has expired. So you will always keep probing these oscillations in the excited state probability because of the way you measure. Does the same work for whole line detection? Well, that's very interesting. So I take my signal out. Now I don't get the clicks, I don't get a strong back action. I have a weak measurement mixing with a strong local oscillator field. But when we do it, it turns out that in the same amount of time, we actually narrow in the Rabi frequency by just the same amount. So whole line detection works fine. What we are doing here is that we are watching the block vector rotate between the north and the south pole with little random excursions because of the back action of the whole line detection. And I'm measuring exactly the component of the dipole which is in phase with that rotation. If I'm a little bit stupid and I measure the wrong production, if I put a phase here such that I measure the component of the block vector who's actually 0, then I don't go near it as much. So this is the same setup, it's the same strength of this flow field, but I'm measuring the wrong phase component. And therefore, you can see the error remains larger for much longer. In principle, the block vector does not even make any excursion in that direction, but due to the back action of the measurement, you are actually kicking the block vector a little bit to the side, and then that component does get sensitive to how fast it will rotate. So this is illustrating that, yes, I mean, some measurement schemes are good, some measurement schemes are bad. Sometimes we can easily understand why. I don't really understand why this homogram detection is as good as the counting measurement, but I can see it from the simulations. And here we have another MATLAB code, but I don't even dare starting it up, but you can try it yourself. It's called Bayes homodyne, and you're just doing exactly the same, but now we simulate the homodyne detection. And your question, of course, was before, you are lucky. There's no way to be lucky here because it's a noisy signal all the time. But you still accumulate that knowledge with the same speed on average. So this was classical fission, right, in my terminology, because this was analyzing how much do I learn from a concrete experimental scheme and from my true experimental record. So this is not asking how well could I, in principle, know the parameter value without specifying which measurement value. So if I would like to know also what is the best you could ever know about this parameter. And that is the so-called quantum deceleration. And that's a very complicated question to ask because the quantum state we actually talk about is the quantum state of your emitting system and all the radiation that has been emitted. That's a field that we have been detecting when we did the analysis of homodyne and counting, but I actually want to not detect it because I don't know what is the best way. So I actually just want to keep the field and look at this big quantum state that contains both the quantum degrees of field of the system and the emitted field. And then maybe if I have one Hamiltonian H0, I will have one state of the system at a given final time and some field stretching from here, and if it's light, let's say I measure for a second, then it's stretching from here up to 300,000 kilometers away, right? Because that's the speed of light. So within that distance, from here to 300,000 kilometers away, there are photons. But these photons are quantum mechanical. They are all over the way. They are superposition states of being here or there or everywhere. That's what I indicate by these crazy waveforms you see in this space. And two different Hamiltonians would give rise to two different such states of the whole universe, of the emitter and the big radiation. And the best detection you could imagine to distinguish these two cases would actually be joint measurement of the field and the emitter in some preferred basis. Let's just pretend that we know the wave function. But then to distinguish these two global quantum states, I just know that I have already the possibility to think of it as being two vectors with a certain scalar product, a certain overlap between the two states. So in principle, the best detection is the one I described before. This is quantum state 1, this is quantum state 2, and if I can calculate that overlap, that will tell me how well I can distinguish those two cases. But it's of course impossible. And it's impossible because we really don't know how to calculate that state. I mean, that state has never been calculated by anybody. It's super big Hilbert space, because it's a Hilbert space that contains maybe millions and millions of photons who can be anywhere. They have not been detected yet. So this is why we do the reduced density matrix. This is why we use the quantum trajectories to eliminate this part of the dynamics and look only at the small system piece of freedom. But for the quantum fission information, I actually need to know the overlap between those two enormous states. So, how do I find that overlap of these huge quantum states? So I'm a little bit proud of this because it's not very difficult what I'm going to tell you, but I think it's a very clever trick, and I got it myself, so on that day I was very smart. So I'm doing it the quantum information way. So instead of saying that you ask somebody, your worst enemy, to either apply Hamiltonian 0 or 1, and let you guess which one it is, we let a quantum ancilla, who has two possible states, decide to apply both H0 and H1. So that if the ancilla is in 0, the interaction between the subsystems imposes H0 on the system, and if you are in 1, you impose H1 on the system. It's not as crazy as it sounds. So I mean, I guess Christian will tell us later about maybe the electron spin in an NV center probing the state of a nearby nuclear spin. And how can you do that? Well, because if the nuclear spin is down or up, there's a magnetic field interaction on the other system who depends on that nuclear spin state. Or at least you can do that in some of these spin systems. So in real physical models, this actually often happens, that this system is exposed to a Hamiltonian who depends on the state of this ancillary degree field. For me, it's just a mathematical trick. So I'm just saying that, now let me introduce this two-level system. The evolution under the Hamiltonian brings me into this superposition of 0 times psi 0, which is exactly what I get subject to H0, plus in superposition 1 with psi 1. So that's the state of my ancilla plus the system plus the big environment. So of course, I haven't made life any easier by now. These are still quantum states I cannot really calculate. But now there's a nice little trick here, because the overlap between that state and that state is actually the same as the mean value of the Pauli lowering operator between 0 and 1. If I take this state and I try to calculate the coherence between 1 and 0, then it will be exactly the scalar product between those two states. In quantum information, we know this very well. We call it decoherence. We say that if 0 leads to a different state than 1, then you lose the superposition of 0 and 1. The environment is watching, and in some sense knows whether you are in 0 and 1. And the more the environment knows, the less you preserve of the coherence between those two states. But it's just a mathematical exercise, right? I mean, you can see that the overlap between that state and that state is going to contain cross terms, and if I want to know the lowering operator, this will take 1 to 0, but psi 1 and psi 0 will have a scalar product with it. So the scalar product between my two huge states is the same as a simple expectation value of just that small system. And I'm not proposing an experiment, but I'm proposing a trick now. Because this little joint state of the ancilla and my small quantum system, if I know that state as a density matrix, I can also calculate that mean value. And this small quantum system is coupled by damping to this big environment. But that just means that I can solve the system by density matrix. So I solve the density matrix problem for this ancilla enlarged system of ancilla plus my quantum system using these two different Hamiltonians. But I can trace out this environment because that mean value is a mean value belonging only to the small system. So the density matrix for this blue part of the system is a small set of equations. I don't need to deal with the Hilbert space of many photon states. I only need to deal with this two-level system. And if this is also spin 1/2, then it's two two-level systems. There's 4 product state components. There's a 4x4 density matrix. It's super easy to solve. Okay, so this is a proof. I know this is heavy, but it's also nice because we can actually do it. So That density matrix equation leads to a master equation. The master equation has one term which is the important, so that's the 0, 1 block, which is looks like a master density matrix for the small system, but in fact it's off-diagonal elements because it's between 0 and 1, or this is 0. And the theory is actually coming out very nicely, because the trace of this little matrix here, that's going to be this overlap between the two states. And that trace is going to decrease from 0 to 1, from 1 to 0, indicating that the two states become distinguishable. The equation looks like this. This looks like the master equation that Maury has been writing down and I've been writing down in our first lectures. But it's not exactly the same equation, because you can see here that I actually different Hamiltonians from the left and the right. So that's a structure you get because you have these two different auxiliary states. So this is a funny master equation. It doesn't preserve the trace, luckily, because that's exactly the measure I'm looking to look for. So I'm acting with a master equation with different Hamiltonians, and if the quantity I want to estimate is associated to decay rates, I should actually also allow these jump operators to be different when we act on the left or on the right of the density matrix. So this is a super easy equation to solve, and when we have solved that equation, it's just the size of the master equation. Then we know these probabilities. So I have to wrap up here, but here I have a two-level transition, and I ask myself, is it driven or not? Is the Rabi frequency equal to 0, or does it have a particular value? And what you see by photon counting, you can gradually remove the error probability of that assignment. So this is a classic efficient. And it just says that the error probability is going to be reduced because either you have no click for a very long time, and then you would, of course, asymptotically know that you were not driving the answer, or there's a certain possibility that you have had a click, and then you can rule out the 0 value. That's the blue curve. The green curve is if you only measure the final atomic state. And the final atomic state is going to be the steady state if you don't look at the line. So at the end, you would want to see, can I see the difference between an atom whose ground state or half excited? And you cannot precisely see the difference between the ground state atom and a half excited state. That's going to be an error probability, which is here at quarters. The black curve is the interesting one. That's the quantum Fisher. That's the one who tells us what is the best, the smallest error probability you can get. So any strategy you might invent will actually always be above or close to this black curve, because that's the most information which is available in the surroundings of your little quantum system. So that's really what I wanted to show here. Of course, we would also ask, what if there's more than 2 hypotheses? There could be many hypotheses. That's actually a difficult problem. It's already a difficult problem to distinguish which out of 3 states or 4 states or 5 states are given to you. So I told you we know what to do in the case of 2. We don't really know analytically what to do in the case of 1. We had a discussion about that yesterday. But it's possible to do it numerically and also very efficiently. And the same way, I can extend this little trick I showed you to the case where I have multiple Hamiltonians, and I want to distinguish these multiple Hamiltonians, and then by the same trick I just showed you, we can also distinguish them optimally the same way. This is a paper we put on the archive, it's just at the beginning of this week, so this is really actually Sunday. And so this is something that we are really working on now. In this case, for example, here, what is the probability you make an error if you try to guess if your Rabi frequency is plus or minus omega or plus or minus I omega? Okay, so you actually excite the atom as much, but you excite it with different phases. And looking at homodyne detection, you can, of course, in principle see the difference between the excitation phase, and as function of time, you do reduce the error probability in telling which one is the actual one applied to your system. But it's really a little technical. So I'll come to my conclusion. The state of a quantum system is conditioned on the probing outcome. This is what we call the quantum trajectory. And if you go into metrology and hypothesis testing, then you can implement that in this Bayesian manner via the trajectories, because the trajectories do whatever they do, but they also have always a known probability for giving the outcome you actually see. And that probability, by Bayes' rule, you can convert back to re-estimate what's the probability for the different parameters. We use in this trajectory story very much the fact that the trajectory, the measurement themselves, induce transient response. Your system is never in steady state. It's constantly being quenched, and the fact that it's constantly being quenched by this measurement back action makes it much more sensitive to the parameters you're looking at. So this is really an inherent part of this thing, is that you're kicking the system every time you learn something, and those kicks makes it more sensitive. So it's almost magic. It's a free gift that your measurement is also helping you in increasing sensitivity. And then we have this quantum thing where I don't even talk about measurements, but I call it a golden standard, namely the quantum information that can be extracted. It's relatively easy to calculate it, but it's not so easy to find out how you actually achieve that limit. Because I didn't tell you the measurement, I just told you that this is the best measurement you would ever do if you had the world's largest detector that could measure anything. Does the fish information grow as t or t squared, or any other power of t? If it grows with t, which is typically the case, your error bar will go as 1 over square root of time. But you could easily imagine regimes where it goes as other power. Does it grow with the number of particles if you have an interaction system, or does it grow with the number of particles squared? That's also the question that Maury asked yesterday. And these are really the questions that we are trying to resolve these days in this sort of metrology. And with this, I think I've finished. Maybe just one last remark, that everything I did was just taking a static situation. Of course, you would also ask yourself, are there good Hamiltonians you should add on top of the one you want to sense? Maybe driving the system with some other Hamiltonians will increase your signal dependence on the parameters you're interested in. And that could probably be cast as an optimal control problem. The same way as there are optimal control people who make perfect state-to-state transfer, you could go to optimize efficient information. And this is, I think, one of the super interesting challenges for the future. So with this, thank you for your attention.
Thank you.
Let's go back to the PRL paper.
Yes, so the one with the one edition.
Yeah, and I get lost. Go one size more.
Yes. It's also difficult, yes, but I could write that.
Okay.
Yes.
So eventually we have a superposition of 0 plus 1. And
yes.
How does the entangled state show up?
It shows up because there's an interaction between the two systems in the sense that if you are in 0, you are acted upon by H0, and if you are in 1, the system is acted upon by H1. So for example, if this is spin down, it gives a magnetic field pointing down, and then this one is feeling a downward magnetic field, and if this one is up, you feel an upward magnetic field. So you're processing according to 2 different Hamiltonians depending on this. And of course, there's a theory tool, because here it's only a theory tool. I just call this a controlled interaction, the same way as if you do controlled not operation in a quantum computer. I can do here controlled do nothing, controlled rotate your qubit, or whatever you like.
So here we want to find out the Hamiltonian is H0 from H1.
Yes, exactly. And as I say, the difference between H0 and H1 is really encoded in this big space, because that's where the state has evolved. It's a joint state of the system in the surrounding field, and that's where most of the information is sitting, of course, in this field, because that would be 1 second of data record. And of course, that's where the information is sitting. It's just that that quantum state is huge. I don't know how to write it down. But the overlap between those 2 wave functions is actually the same as the decoherence of that qubit due to this matter. So therefore, I just turn that into a different problem, namely the problem where this quantum system composed of these 2 decays into an environment. I can solve it with a master equation, and therefore I can compute what happens to this decoherence. So it becomes a standard decoherence problem solved in this particular way. And it's just a theory trick. I mean, this is not something, don't do this in the lab. I should avoid it. Don't try to do this in the lab. This is something I do with my computer. In your lab, you are like A0 or H1. And then I just tell you how well you can use that for sensing.
So does that mean that this strategy requires the states you're trying to get your hypotheses to have some, like, that has to be a particular hypothesis that has some available entanglement that you can apply. Are there some hypotheses where this would work?
I mean, this subsystem here could actually be prepared in any initial state, of course. So at time 0, it could be a product state of these 2 and some initial state of the system. This system is purely fiducial. It's just something, a theory trick, right? So the real system is this one. So you prepare the initial state, and then you ask yourself, after some time, how well can I see which Hamiltonian act? And then what is happening in this crazy model with this artificial ancilla is that it has turned into an entangled state of those 2. And that entanglement is actually not of those 2, it's of that one together with the whole world in this box. But that big entangled state has mean values for this guy, this decoherent, and that decoherence is due to the entanglement between that guy and the environment. And this is what we try to fight in the quantum computer. But that's exactly what you learned also. In the quantum computer, we try to fight decay. We try to fight interaction with the environment. And if it happens, we call it decoherence. So here I just say, wow, that decoherence, that's actually the number I want to calculate. So I turn this into a little quantum computer, a little imperfect quantum computer one, and then I can calculate it. Yes?
If you introduce the second antenna,
yes,
does it improve?
No, this cannot. I mean, so because this gives me exactly that scale up, and that's all there is to know. But of course, your question may be interesting in the sense that I could introduce a larger ancilla system. Because if I have 4 hypotheses, I also want the ancilla system to have 4 states. So therefore, including more complicated ancillas will allow me to treat more and more hypotheses at the same time. So this would be one way to do it. You can also just take the pairwise, because the only thing that really matters if you want to discriminate 4 states is the mutual scale-up product between any 2 of them. So you will also do the previous calculation 2 and 2 and 2 for all pairs, and that will give the same information.
So you had a slide where you had some data probability of the parameter given the data from the simulation and then an analytical fit to it.
Yes.
So I was wondering, so you said that you could calculate the official information because in this case you could find an analytic expression for the probability. So in practice, suppose you have a system that's complicated and you cannot get an analytic expression. It seems that in order to evaluate a derivative like that, you really have to keep computing the solution to the master equation over and over again for infinitesimal separation to the current.
You're absolutely right. I mean, this problem is a very special problem because every click puts you back to the same ground state. So there's only one function because you need to know what happens out of the same ground state. And that's this red curve. But of course, if your measurement back action kicks you into all kinds of new states every time, depending on where you are before the click, you are exactly right. And so we have actually one of these papers, we are exactly outlining how you can do that averaging, because you may still want to do it. You know, metrology is actually not about the value you measure. It's about the error bar. Well, that's not true. You want to know the value, otherwise you wouldn't measure it. But the art in metrology is, of course, to make the error bar as small as possible. I mean, Holger's talk, he told us about the error bar all the time. Who cares what is the value of the phi structure constant? But if you want to tell it to me, give me 9 digits. And so that's the same here. So this is an important entity. And maybe we want a theory to tell us how to put that error bar. And so one candidate to that error bar is, of course, what we get from base. Oh, I have to go in forward direction. There. So there's, of course, a width. And that is an indicator of the error. But you have to be very careful with that one, because this is what is called a maximum likelihood estimator. The width of this distribution is not exactly the same as the error bar of your estimate. So there you have to be careful. But I mean, so we like to have a separate analysis who gives us the error bar. We heard it in your talk actually yesterday, in Maury's talk, that you make a separate assessment. How much will fluctuations, the natural fluctuations in your experiment, affect the uncertainty? And we like to have an analytical formula for that, and that's what we got yesterday. And this is what we can also simulate, just as you say, from the master equation. We should take a 5-minute break, but I think this is a very natural opportunity for you to come forward and discuss it with Klaus. You have 5 minutes. Yes. Thank you.